we need to learn how to write balanced chemical equations. This is called balancing by inspection, which means you look at it, you inspect it, and you figure out what you need to do. The book gives us guidelines, but there's no one best way to balance an equation. So, when you're first getting started, follow the guidelines, but sometimes you just have to ditch those and do your own thing. So, your book says the first thing to do is write a skeletal equation by writing the correct chemical formulas for each of the reactants and products. You have to start out with the correct formulas. Okay? If the formulas aren't right, everything else is going to be wrong. You can review it, chapter 5 if you need some help with nomenclature. If an element occurs in only one compound on both sides of the equation, try balancing that one first. If there's more than one like that, balance metals before nonmetals. This is just a guideline to make things easier. It's not a hard and fast rule. If you see an element as a free element on either side, like oxygen in that last one, there was O2, leave that one for last. The reason you want to do that is because you can fix that one at the end without messing anybody else up. After you've balanced it, if you end up with fractional coefficients, you need to clear those out by multiplying the whole thing by an appropriate factor, and I'll demonstrate that. At the end, check to make sure the equation's balanced. So these are very important. You do change the coefficients to balance the chemical equation. You do not change the subscripts. It is tempting sometimes. Like, oh man, if water was H2O3, it would be balanced. But you can't do that. Okay? You can't change the formulas. You can only change the coefficients. You can only change the coefficients. So let's do this example. Write a balanced chemical equation for the reaction between solid copper and solid sulfur to form solid copper 1 sulfide. So this is pulling from chapter 5 with the nomenclature. We have to be able to write some equations, some formulas. So copper, what's the symbol for copper? Cu. And this time we're going to write the state symbols just as a little bit of practice. They're telling us solid copper. So then I'm going to put S in parentheses. Solid copper and sulfur. What's sulfur? S. And it says that's solid also. Is sulfur one of the diatomic elements? Horses need oats for clear brown eyes. No, it isn't. So just S. Not S2, just S. Those are the reactants. To form, that's the arrow. And then copper 1 sulfide. Well, copper 1 is copper with what charge? +1. The Roman numeral tells us the charge. Sulfide is an ion, and what charge does sulfide have? You have to look at the periodic table. -2. So 2 minus. And then we look at the charges on these guys. This one's -2, this one's +1. They are not the same. You could do the crisscross thing, and you're going to end up with Cu2S as your formula. Cu2S. And it says that's also a solid. So that's the first step, is to get those done, the formulas. Sometimes that's done for you. The next thing we need to do is look at it and figure out if it's balanced or not. Here we have 2 elements that are by themselves on this side. We could start with either one. I generally start with the first one. So here's Cu. How many copper atoms are on the left side of the arrow? 1. And how many are on the right side? 2. So we can fix that by putting a large 2 in front of Cu. That says we need 2 of these guys. We need 2 copper atoms. We don't want to make it a molecule of Cu2 because that doesn't exist. We're not going to do anything with the subscripts. You get your chemical equations in place, and then you leave them alone. Okay? You can do something in front. You can say, well, I need 5 of them, but you cannot change what they are. So now we've got 2 coppers on the left and 2 coppers on the right. How many sulfurs on the left? And how many on the right? And there we go, we're done. Balanced chemical equation. Any questions? Yes? Do you need to leave the solid in parentheses? It didn't specifically say to include state symbols. And so my thing is, if the question says include state symbols, like it will on the next lab that we do, then you have to write the state symbols. If it doesn't specifically say, then you could leave them off. We're just doing it for practice. They don't actually affect the balancing at all. Any other questions? Let's do another one. Write a balanced equation for the reaction between sulfur dioxide gas and oxygen gas to form sulfur trioxide gas. We need our formulas first. Sulfur dioxide. What kind of a compound is that? Is it molecular, ionic, or an acid? It's molecular, right? One of the clues is this di in there. But sulfur is a nonmetal and oxygen is a nonmetal. And so the prefixes are what tell us how many. So sulfur dioxide means SO2. It tells me it's a gas, so I'm going to put G. And oxygen gas. Oxygen is O. Is oxygen a diatomic element? Horses need oats for clear brown eyes. Yes, it is. So then we need to put a 2 on it. This is where we really need that sentence to remember the 7 diatomic elements. I'm probably making all of this too large and it won't fit. Sulfur trioxide. Well, that's sulfur and 3 oxygens, and that's also a gas. The state symbols have nothing to do with balancing the equation. And they do not all have to be the same. They just are what they are. So now, if we look at this equation, we see that everything has oxygen in it. But we have oxygen here by itself, and so that's a good indication that we should leave oxygen for last. And here we have sulfur only in one thing on each side, so that's a good thing to start with. So we look on the left side and we see I've got 1 sulfur. Now, one technique that some students find helpful is you can kind of make a tally sheet underneath. Draw a line. See that okay? Draw a line where the arrow is. And then list your elements. We've got sulfur and oxygen. So we've got sulfur and oxygen. I'm just going to go through and tally up how many I've got. So in this compound, I have 1 sulfur and I have 2 oxygens. Just looking at the formula. And then in this one, I've got 0 sulfurs and 2 oxygens. And over on the right, I've got 1 sulfur and 3 oxygens in this compound. This can be really useful, especially for more complicated equations. Now I can compare 1 plus 0 on the left is 1. 1 sulfur, and on the right I have 1 sulfur. So the sulfurs are fine. On the left side, I've got 2 oxygens and 2 oxygens, that's 4. And on the right, I have 3. What can I do about that? We could use fractions. If we put 1/2 in front of oxygen here, that would make this a 1, wouldn't it? Half of 2 is 1. Most students don't like introducing fractions. They don't like dealing with fractions that are there to start with, so why would we want to add fractions to something? So let's not do that. If making using fractions makes sense to you, you go right ahead and do it, because you can do it that way. So here we've got 4 on this side and 3 on this side. This is an odd number, isn't it? And these are coming in 2s. And so this side's even and that side's odd. I call this the odd-even problem. Isn't that a very creative name? This is the odd-even problem. What happens when we double an odd number? It becomes an even number, right? So when you get a situation like this, it happens a lot in combustion reactions where you've got odd on one, even on the other. Double everything and then see what happens. And it usually works out pretty well. Let's go with that color. So I'm going to put a 2 here. And so that's going to make this 2 and this 4. And I'll put a 2 here, and that'll stay 0, and this will be 4. And I'll put a 2 here, and this will be 2, and that'll be 6. I just doubled everything. I did this a little different than I usually do it. Usually I say, we were trying to fix the oxygen, so let's not put anything in there, and I should have stuck with that. But let's just deal with the mess I made here. So the sulfurs are the same. Doubling everything didn't change them. Oxygens now, I've got 4 plus 4, 8 on one side and 6 on the other. What if I didn't have a 2 there? Would that make things better? Yeah, it would. If I erase this 2, then I've just got 2 oxygens there. And 4 plus 2 is 6. So now I've got 6 oxygens on the left and 6 oxygens on the right. I have to remind myself not to do it that way again. Any questions? Another example. We need lots of examples for these. Write a balanced equation for the reaction between aqueous hydrochloric acid and solid manganese for oxide to form aqueous manganese 2 chloride liquid water and chlorine gas. Question?
On the last one, because they equaled out when you double them,
Mm-hmm.
they can stay as 2, but if they didn't, then you have to go to like 3 or 4.
Yeah, if doubling these did not solve my problem, I would end up with probably needing a coefficient in here. Sometimes you'll have to put a coefficient on the oxygen. I think we'll come across one of those later. Yeah, doubling things doesn't fix it usually. It did fix it here. But what it does is it gets you away from the odd-even problem, where you're trying to find half a pair of shoes, basically. I think of oxygen as like being a pair of shoes. You go to the shoe store, you have to buy 2 shoes. They won't let you just buy 1. You have to buy 2. And so if we only needed 1, we've got a problem. And so that's where the doubling helps. Okay, let's look at this one. Hydrochloric acid. We're getting a review of nomenclature. The prefix hydro tells us that this is a binary acid. The oxyacids do not have the prefix hydro. So hydrochloric means it's hydrogen and chlorine. So chlorine has the charge -1 based on its position in the periodic table. And so we just need 1 hydrogen to balance that. So hydrochloric acid, HCl, and that will be aqueous. And then manganese 4 oxide. That's an ionic compound. Manganese is Mn, magnesium is Mg. Manganese, and the 4 tells us the charge is 4 plus. Oxide is oxygen. We know from its position in the periodic table that it's -2. We've got +2 and -2. This is one where crisscross can mess you up. Crisscross would give you Mn2O4. But is that the lowest ratio? No, it isn't. The correct formula is MnO2. You need 2 oxygens to make -4 to balance the +4. Crisscross works most of the time, but not all the time. So it said that was solid plus, and when I'm writing these, I am leaving space because I know I may need to put a coefficient in there. Manganese 4 oxide to form, there's the arrow, manganese 2 chloride. So that's Mn2 plus with chloride, which is Cl minus. Crisscross is fine here, MnCl2. MnCl2 says that's aqueous. And liquid water, H2O, and chlorine gas. And chlorine gas. Is chlorine a diatomic molecule element? Yes, it is. Cl2. And that's a gas. I ran out of room. Oh, sorry, he's off the screen a little bit there. There's a Cl2 over there. So there are the formulas. And now we need to balance this. So let's try that tally method, and we'll draw a line down the middle here. And I'm just going to go through my reactants and list the elements. So I've got H, and I've got Cl, and I've got Mn, and I've got O. When you first start balancing equations, this might be a useful method, but after you get the hang of it, you won't need to do this anymore. So here in HCl, I have 1 hydrogen and 1 chlorine and no manganese and no oxygen. And over here in MnO2, I've got no hydrogen, no chlorine, I've got 1 manganese and 2 oxygens. Over here, 2 chlorines, 1 manganese, and no oxygen. In the water, I've got 2 hydrogens and no chlorines, no manganese, and 1 oxygen. And over here on this guy, I've got no hydrogens, 2 chlorines, no manganese, and no oxygen. Because things are getting all jumbled up in this one, aren't they? This one's more complicated. So writing these out can help us to see what we're dealing with. Here we have chlorine all by itself, and so we may want to leave chlorine for last. Hydrogen's in one place on each side, oxygen's in one place on each side, and manganese is on one place on each side. So let's just start with hydrogen. If you start with one element and you get going and you feel like you're running in circles and you are finding yourself changing things you've already changed, stop and start over with a different element. So hydrogens, I've got 1 hydrogen over here, 1 plus 0, and I've got 2 over there. So I will put a 2 in front of the HCl, and now I'm going to adjust what's underneath, because now I have 2 hydrogens and 2 chlorines. And I'm going to look at it again. I've got 2 hydrogens over here and 2 over there, so the hydrogens are taken care of. I'm going to leave the chlorine till the end. So I'm going to skip him. I'm going to go to the manganese. On the left side, I have 1 manganese on the left and 1 on the right. So that one's okay. And then oxygen. I've got 2 oxygens on the left and only 1 oxygen on the right. So I need to put a 2 in front of the water molecule. And that's going to change the hydrogens and the oxygens. So I fixed the oxygen, but in the process of doing that, I messed up hydrogen, didn't I? Now I've got 4 hydrogens on the right, and I only have 2 on the left. So I have to go back and fix that. So I'm going to erase this 2 and make that a 4. That gives me 4 hydrogens and 4 chlorines. Now I've got hydrogen and manganese and oxygen taken care of, right? You can look and double check. Now we're going to go finish up with chlorine. On the left I have 4 chlorines, and on the right I have 4 chlorines. They took care of themselves. That happens a lot. The last guy takes care of himself. So there's our balanced equation. Any questions? Write a balanced equation for the reaction between liquid benzene and gaseous oxygen to form carbon dioxide and liquid water. So they're giving us the formula for benzene, C6H6, telling us that's a liquid. What's the formula for oxygen? O2. And that's a gas. And then to form tells us that's where we need our arrow. Carbon dioxide. What's the formula for carbon dioxide? CO2. What would be the state of CO2? Carbon dioxide is a gas at room temperature, right? So let's think about it. Here we've got benzene reacting with oxygen. That sounds like a combustion reaction, something burning, doesn't it? So this is definitely not going to be a cold reaction. It's either going to be room temperature or most likely above room temperature. And so we can kind of guess at the state, even though it didn't tell us what it was. And then here is telling us liquid water. The formula for water is H2O, and that's something you just have to memorize. Water has a special name. Should we make the little chart underneath, or should we just go for it? Anybody have a preference? Do you like the chart?
Yeah.
We'll go with the chart. So we've got carbon, we've got hydrogen, and we've got oxygen. And those are the only 3 elements we're dealing with. I'm going to draw this line at the arrow because that's where we're trying to balance things. We need the same number of carbon atoms on each side. You can think of this as being like a teeter-totter. And you have to have the same number of carbons, hydrogens, and oxygens on each side to have it be balanced. I hate it when I do that. There we go. So in C6H6, we have 6 carbons and 6 hydrogens and no oxygens. In O2, we have no carbons, no hydrogens, and 2 oxygens. In CO2, we've got 1 carbon, no hydrogens, 2 oxygens. And in the water, we have no carbons, 2 hydrogens, and 1 oxygen. I'm just taking inventory. So we want to leave oxygen for last because oxygen's by himself here. And so that makes him easy to adjust because we can fix him at the end and it won't mess everybody else up. So let's start with carbon. 6 carbons on the left and only 1 on the right. So what do we need to do in front of the CO2? Put a 6. And that changes all the numbers underneath. So we have to multiply the 1 by 6. We get 6. And we multiply the 0 by 6, and it's still 0. And here we've got 2 times 6 is 12. Carbon's taken care of. Now we'll look for hydrogen. I've got 6 on the left side and only 2 on the right side. How can I fix that? Put a 3 in front of the water. And that changes everything underneath. So we've got 6 and 3. And don't turn your common sense off here. Look at 3 H2Os. This is like 3 bicycles. The H's are the wheels and the oxygens are the frames. And so we've got 6 wheels and 3 frames in the 3 bicycles. So carbon's good, hydrogen's good, now we have to take care of the oxygen. So there's 2 oxygens on the left, and how many oxygens on the right? 15. Right? 12 plus 3 is 15. And on the left we've got 2. What did I call this sort of a situation? A mess. This is an odd-even problem, right? We need an odd number of oxygens, but they're coming in pairs. So the solution to this, we are trying to fix the oxygen, double everything else. So I'm going to multiply everything but that O2 that I'm working on by 2. Oh, that doesn't show up very good. I'll use a different color. How about pink? Can you see pink? Yeah. So I'm going to put a 2 there. I'm skipping this guy because this is the one I'm messing with, and I made a big mess last time. This is a 6. I'm going to double that, and that's going to be 12. This is a 3. I'm going to double that, and that's going to be 6. Now that changes all the stuff underneath. So now I've got 6 of these water molecules. That gives me a total of 12 hydrogens, right? And it gives me 6 oxygens. And here I've got 12 carbons and 24 oxygens. Don't be alarmed that the numbers are getting big. It happens. And over here on the left, when I do 2 of these, then I've got 12 and 12. So now I've got 24 plus 6 is 30 oxygens, right? 30 oxygens, and over here they're coming in pairs, so I need 15 pairs. I need 15 of these to give me 30. And that's how the odd-even doubling everything works. Any questions?